to this mini symposium. And I want to talk about this numerical method called the reproducing kernel collocation method from both the concern of rigorous numerical analysis and also the concern of computational efficiency. And in fact, we began the study of these RK collocation methods instead of using the finite element or Galerkin methods for non-local models. Because of the high computational cost you have to pay for implementing finite element. So, and also I am from a numerical analysis background, so I am also concerned about things like proving convergence of solutions. Okay, let's see. First I have to say that this is a joint work with Dr. Yu Leng, who was a PhD student at UT Austin, but now a postdoc at Purdue University, and also Dr. John Foster from UT Austin and Nat Trask from Sandia Lab. And I also want to mention that this is a work that is done when I was in UT Austin before moved to San Diego. So I thank the support of Department of Math and Oden Institute, and also want to thank the support from NSF. Okay, so this is the outline of my talk. In the introduction, I want to emphasize on a class of numerical methods called asymptotically compatible schemes. Some of you have heard of it many times. Now, then I'm going to introduce you the reproducing kernel collocation methods. And then the next, the so-called quadrature-free RK collocation methods are just modifications of the RK collocation methods for further reduction of computational cost. And then you'll see what they are. And then in the end, is summary. So first, the peridynamics model, I believe I don't need to introduce this anymore. And we've already seen some introduction today, a lot of introduction today. So I'm going to skip those slides to save you some time. But I do want to mention that I'm only going to look at the linear models. So for example, this linearized bound-based operator, and also for acting on a vector field U. And if U is a scalar function, that is what we've called this the non-local diffusion operator. And as delta going to 0, as we know that this bound-based peridynamics model converges to the linear elasticity equation with certain Poisson ratio. So that's why we also have this state-based model. And this is one way of writing the linearized state-based operator. And it has two parts. One part is for the bound-based part, and another is a non-local analog of the gradient of the divergence of U. So here, D delta and G delta are the non-local divergence and gradient operators. And you can write them down like this. And this theta, which is an intermediate variable, this is what people call the non-local dilatation. And actually, you could, if you introduce this intermediate variable, you could write an equivalent form of the state-based model in a mixed form. And so with this state-based model, we have the convergence of it to the most general linear elasticity with this general arbitrary Lamé constants. So the non-local equation as delta going to 0. And here's the important kernel where it should have this scaling, where D is the dimension. And with this scaling, we see that the second moment of it is a constant, which is the same as the second moment of K. And so then we have the solution space, which is defined in L2 with this double integral to be finite, and I impose the 0 Dirichlet boundary condition, but in fact, we can impose any non-zero Dirichlet boundary condition. And so also we have this non-local Poincare inequality, which ensures the well-posedness of our equation. And here I write it down because I want to mention that for the Galerkin scheme, for the finite element or finite element scheme, it inherits this kind of stability naturally. And but for a collocation scheme or a finite difference scheme, you don't have naturally the numerical stability. Now, we also know that as delta going to 0, the solution converges. U delta converges to U0. Now, so for the asymptotically compatible schemes, we call a scheme to be AC if it satisfies all these ways of convergences. Note that I use U delta for the solution of the non-local equation, and U0 is the solution for the corresponding PDE, and then U delta H is the discrete non-local solution. And if I fix a delta and let H go to 0, and it should converge to U delta, and this way of convergence is what Patrick called I believe the M convergence, as H goes to 0. And in this way, as H and delta both go to 0, it should converge to U0, and this way is what Patrick called the delta convergence. So a nice numerical scheme satisfies all those convergences. And obviously, there are robust schemes useful for validation and verification and suitable for multi-scale simulations. So what schemes are AC? I'll give you this example just to show you an idea of how to find AC schemes. This paper, this 2005 meshfree paper by Dr. Yu Leng and Askari, is a highly cited paper. Now, today I looked at Google and I saw that it's over 1,000 citations right now. So this idea of this meshfree method in this paper is simple, that if I have this non-local operator here, I'm going to write it as a summation of these things where xk's are a collection of nodes, and vk is the volume of the node xk. Now I want to say that for this method, it's convergent with the fixed delta, namely that we test the M convergence, it's convergent, but it's not convergent with a fixed ratio M. So, so why? So I'll show you the reason why it's not difficult. In 1D, you can actually write this approximation. If X forms a uniform grid and H being the grid size, then you can write this approximation in this way. And then you, if you write it in a central difference form, it looks like this. Now just do this so-called quadratic test, and which means that if you take a quadratic function, is x squared over 2, we know that the second derivative of it is 1. And moreover, if you apply the non-local operator on U, it's also 1, because you can write the non-local operator as its centered difference form. And then with this quadratic function, it's just the second moment of the kernel, which is a constant 1. But if you use this meshfree method, you're going to find that this thing is not going to be closer and closer to 1, because you can write out this quantity and use the scaling of k delta, and you get that this is equal to this quantity, where if m is larger and larger, this is approximating the integral, this integral of second moment of k here. But if m is fixed as a constant, that's what we test for the delta convergence. If m is a constant, then it's just a constant depending on what m is, and normally it's not equal to 1. So you see that as delta and h both go to 0, if I have a fixed ratio m, this thing is never going to be closer and closer to 1. So there's always an arrow. So In other words, this method doesn't pass this quadratic test. And in fact, we found that this test is quite important. Mostly, if a method passes this quadratic test, you probably can show it's an AC scheme. You can show that it's convergent with a fixed ratio M. So obviously this paper is already 15 years ago. So from then we have seen many different numerical methods, and we actually can find AC schemes in each category of those numerical methods. For example, for finite for these different types of numerical methods, we have different techniques to show the convergence. For finite difference, for example, we have truncation error analysis plus the numerical stability, which is established from discrete maximum principle. For finite element, we have the variational framework to show the convergence. Now, those red words are the drawbacks of each type of methods. For example, for finite difference, since we need the discrete maximum principle, and that means that we can only prove the convergence of it for diffusion problems, but not for the peridynamics models. And moreover, we only have those finite difference methods on uniform grades. For finite element, those are quite general methods, and we can actually show the convergence for a very general type of problems. But the drawback is obvious that it has a very high computational cost because you have to do numerical quadrature for integrals. Now in 1D you have a double integral. In 2D you have a quadruple integral, right? And then obviously that's not what people want to do, and finite elements are not adopted by any actually practitioner, I believe. So then we have mesh-free methods, but we only have truncation error analysis because in this case, in most of the cases, we lose discrete maximum principle, and we don't have variational framework for mesh-free methods. So in general, we didn't see much stability analysis for those methods. And in some special cases, mesh-free methods, for example, uniform grades can be equivalent to finite difference, but in general, you don't see that, you don't see numerical stability. And for spectral methods, obviously it only works for problems with periodic boundary condition. So our goal is to try to find a numerical method that can be applied to general boundary conditions, at least for Dirichlet boundary conditions, and also that we can prove the numerical stability of that. And it is computationally efficient. And also we wanted to work for the general peridynamics models, and hopefully not just uniform grades. So that's why we start to look at this archaic collocation methods. And first we have to know what is the RK approximation. And this is something like this. If you give me a function u, then I could give you an approximation of u, which is denoted by pi hu, and that is given by a linear combination of some basis functions phi k. And these basis functions are generated from a collection of data points xk. And on this graph, this black dots are xk's. And using this xk, you can there's a way of generating the basis function phi. And for example, if I have a point I here, then the basis function corresponding to this point is a function that is supported in a ball of radius epsilon, something like this. And this epsilon is proportional to h, which is the average distance between those points. Then there's an important concept called the reproducing condition, which will give you whatever order of the approximation. And this, for this reproducing condition, it means that if you have a polynomial of degree less than or up to n, right, you want this approximation to be exact. Now, if this reproducing condition holds, then you could approve the approximation order, something like this, h2n plus 1, and that is, in general, is this order. But there are some super convergence of this method for special cases, but in general, it's this one. So what is a collocation method? Then if you have this approximation, RK approximation, then we look at this non-local equation. Now, this is, let's first take non-local diffusion, right? For a zero Dirichlet boundary condition on omega delta, which is the layer around, delta layer around omega. And this is the same as writing U delta equal to 0 everywhere outside omega. So sometimes I'll just write a U defined on the whole space because those two things are the same. And also zero condition can be, you can also use non-homogeneous Dirichlet condition. Now, if you have a data set on RD, then I can generate an RK basis functions phi k, right? And then I'll write the solution space as expressed by linear combinations of this phi k, such that those coefficients ak is 0 for those k such that xk is not in the domain. So by seeking a solution in this solution space, I'm effectively imposing a zero boundary condition approximately. And the collocation scheme is just to find such a solution in this space, such that this equation holds at the nodes, at the data points xk's. So this is our method. And if you want to look at the collocation method for state-based model, then it's similar, but for state-based model, we have two delta layer as a boundary condition, right? But it's the same that is equivalent as writing it as the boundary condition for every x outside omega. And then the only change is that it defines the finite dimensional solution space as this combination where A is now a vector instead of a scalar. So then U is a vector field. Then you seek for those solutions in the solution space, and that holds on the grid points. But here, I want to mention that this is not simply by substituting this U with this U delta in this equation, because I insert a pi h in between G delta and D delta. And the reason is that after we compute D delta U delta H, then it's no longer in the space as delta. And I want to map it back to a function that can be expressed by these basis functions. And then that's easier for me to evaluate G delta of those functions. So that's the method for the state-based model. Now I'm going to talk about, okay, I've used 20 minutes already. Okay. Now I'm going to talk about some numerical analysis where if you want to have a robust scheme, you need the uniform consistency and the numerical stability. Now the uniform consistency means that if you apply U delta on the approximation of U, then the difference of it with L delta U should be bounded by a constant C times certain order of H, and this constant should not be dependent on delta. So for a method that is not AC, usually what you're going to see is that you have H over delta type of convergence. But now we want this C to be independent of delta. And then for numerical stability, this is something like the inverse of L delta is bounded in L to null. Okay, so the numerical stability is actually harder. So I want to talk about how do we prove it. And in order to prove it, we actually have to restrict ourselves to a semi-Cartesian grade, which means that xk is looking like this. And the reason is that we use actually the Fourier transform, Fourier analysis. So to compare a collocation scheme with a Galerkin scheme, and for collocation scheme, it corresponds to a quadratic form like this, whereas the Galerkin form, it corresponds to a quadratic form like this for u and v to be expressed like a linear combination of those basis functions. And then you can use Fourier analysis to rewrite these two quadratic forms into this, where you see Fourier symbols. Lambda c corresponds to the collocation form, and lambda g corresponds to the Galerkin form. So then our goal is to show that actually the Fourier symbol of this lambda c is bounded below by lambda g. If that can be shown, it means that you can use the stability of the Galerkin scheme to derive the stability of the collocation scheme. And then for doing this, then you compute this Fourier symbol, and we found that the only difference is that you have a square here, whereas you don't have a square here, where here is a transform of the basis function. So then you need the positivity of the transform of the basis function. And that's where we restrict ourselves again to say that for linear RK approximation, the transform is positive. And if it's quadratic, if n equals 2, then the transform of the basis function is no longer always positive. So we have a restriction again here in order to show the stability. And then in the end, we show the stability with these two constraints. And then I want to go a bit quicker. And then for the uniform consistency, we can also show it. And actually, we just if you look at quadratic functions, it passes the quadratic test. Even though it only reproduces linear function for linear RK approximations, actually we can show that this holds also for quadratic functions, and it holds stronger because although it only reproduces linear functions, for quadratic functions, we can actually show pi hu is u plus a constant. So L delta applied on this is the same as L delta applied on u if u is quadratic. And in the end, we can show it for general u, this holds. So we have both the uniform consistency and numerical stability for us to say the convergence of solutions. And on one hand, if you fix delta, you have the second order convergence in H. On the other hand, you have asymptotic compatibility, which is that this difference is bounded by delta squared plus H squared. Now, a little bit about the quadrature-free collocation methods, just to show you the idea. Now, if you want to implement the previous RK collocation, you still need to do quadrature, numerical quadrature, because you need to know how to evaluate L delta on the basis functions to be able to assemble the stiffness matrix. You need to know how to evaluate this integral. And in practice, people do this by Gauss quadratures. So in the neighborhood of any collocation nodes, you find quadrature points, and you do a Gauss quadrature to approximate this integral. And in this paper, actually, sometimes they use 1,000 quadrature points in the neighborhood, in the delta neighborhood of one collocation node to be able to approximate this well. So, so the question is, can you introduce a scheme that you don't need the quadratures? That's what I call quadrature-free schemes. And the way to do it is that you write down an approximation of L delta hat, that is not the integral, but a summation, and those weights can be pre-computed. Now, then you apply the RK collocation. The same is to find this kind of solution, such that this holds on the grid points, where now this L is replaced by L delta hat, and you see the hat is just a summation, so you don't need to do quadratures. Now, these weights can be computed. Actually, we say that if you have a constraint that the approximation L delta hat is exact for quadratic polynomials U, then we can actually write down the with function exactly analytically, and we say that it's positive. And the positivity actually is also important to guarantee numerical stability, and everything is good for this. And in the end, you can also do that for the state-based model just by finding out what are the approximate operators where those are expressed by summations. So in the end, we have this convergence theorem for these quadrature-free methods, which is that again the distance between the difference between this and U0 is delta squared plus H squared, and because we use the approximate operators instead of a real non-local operator, the difference between this and this is also delta squared plus H squared. Okay, so to sum up, we see that in the peridynamics models, delta plays a very important role where it could be changed. And we want our numerical schemes to be robust under the change of delta. So the purpose of using this RK collocation is that is on the one hand, we want to show some rigorous convergence analysis, and on the other hand, we want it to be computationally efficient to use, easy to use. And we, in the end, we've managed to show some numerical analysis, and also I believe this is not hard to use, especially when you use the quadrature-free version of it. And so that's the end of my talk, and you can find those details in these two papers. One is about diffusion, another is about peridynamic Navier equation, which is a state-based model. And so thank you for your attention. I'll take any questions you have.
Yeah, so Xiaochuan, may I ask a question?
Sure.
Yeah, this is Yue. So yeah, so my question is on your page 24 of your slides. You mentioned that the quadrature, 20.